In this video series, we are going to talk about the moment of inertia of bodies, and we're going to see how to calculate the moment of inertia of various solid bodies. Already, the moment of inertia, just as the name sounds, is the moment of the mass. Inertia was a term that was used by Isaac Newton to denote the reluctance of an object or the resistance of an object to motion. So here, the moment of the mass, if we can say it so, is a measure of the resistance of a body to rotational motion. And this is very important because it enables us to study the rotational dynamics of a body, or of a system of bodies. You know, if you have a mass, you have an object that rotates about a certain axis, you want to know, you want to study the dynamics of the body. In this case, the rotational dynamics, you make use of the moment of inertia. So if we just want to establish a simple comparison, let's say we have a linear motion, okay, and on the other side we have a rotational motion. So the mass in a linear motion is analogous to the moment of inertia, which is what we are going to, which is what we are studying here. Then another quantity, let's say the displacement x, for example, in a linear motion would be analogous to a rotation, and to measure rotation we need an angle theta. Okay. Then if you have, let's say, a velocity v in a linear motion, then the rotational analog of that velocity would be an angular velocity, omega. If you have an acceleration denoted by a, then the rotational counterpart of that is going to be alpha, usually denoted alpha, the angular acceleration. Okay. Now say you want to calculate, let's say, the kinetic energy. The kinetic energy is half mv squared if you're in a linear motion. Then if you are considering a body that's rotating, then its kinetic energy, the kinetic energy of rotation, is given by half times the analog of the mass, which is I, times the analog of the linear velocity, which is the angular velocity squared. So this is how we calculate the rotational kinetic energy of a body. In a similar way, let's say we want to get the work done, okay, W. If you're in a linear motion, then you need to take a force and then multiply that force by a displacement. Similarly, if you're in a rotational motion, then to calculate the work done, we're going to take the torque, usually denoted tau, and multiply it by the displacement, which is, in this case, is an angle. It's a rotation. Okay. Yeah, I'm talking of the torque. So if you are talking of a linear motion, you may want to measure maybe the force that you are applying in the body. If you're in a rotational motion, we don't talk of force, but we talk of torque. The force is the mass times the acceleration. So the torque here would be the analog of the mass, which is the moment of inertia, and the acceleration is alpha, if we are talking of rotational motion. So these are really the various quantities that you can have in linear motion and what they become in a rotational motion. So usually when you have a quantity in a linear motion that you want to express in terms of its equivalent or its counterpart in rotational motion, you just need usually to multiply it by r, which is the distance to the axis of rotation. For example, say you want the velocity, then it's related to the angular velocity by just multiplying a distance r. So this would be equal to this. Similarly, for the angular acceleration, if you multiply it times r, you get the linear acceleration. So a linear quantity is kind of the moment, if you want, of the angular quantity. So that works. Yeah, if you have also a distance, let's say the length of an arc is just theta times the distance to the axis of rotation. But that doesn't work for the moment of inertia I. That works for these three quantities, okay? And yeah, it can also work for the force, like if you have a force here, F, and you want to express it in terms of the torque, then the force is just the torque times R. No, I mean, it's the other way around. So if you have a torque, okay, I didn't express it in the correct way. So what I meant, let me cancel this. So what I mean is that if you have a torque through and you want to express it in terms of the force, then the torque is just the moment of the force. That's the definition of a torque. Okay? And you can see it from this relationship. Yeah, but then does this mean that the mass is I times just multiplying a certain R? In principle, we could expect, let me just draw a line here. In principle, we could expect that the moment of inertia is just a mass times a certain distance, right? Just like the torque, just like we did for the torque. That's what the name suggests when we say moment of inertia. Just that when we refer to moment of inertia, what we actually mean here is the second moment, which means we need to multiply it again times R and not just MR. So in principle, it should be called second moment of inertia, but I think for some reason we just take the short appellation moment of inertia. So the moment of inertia of a body about an axis is actually the mass of that object times the distance from the axis of rotation squared. So suppose you have a mass here, you have an axis here. If you want the moment of inertia of that body about this axis delta, just multiply the mass times the square of the axis of, times the square of the distance from the axis of rotation. Now, if you have a mass distribution, so suppose you have just an object that has a certain mass distribution and you also want to calculate its moment of inertia about an axis delta, then in this case, you need to calculate the moment of inertia of a tiny element, dm, okay, of this mass distribution, and then the total moment of inertia is going to be obtained by integrating the moment of inertia of this tiny element. So suppose this is r, then you're going to have r squared times the mass dm, and then you integrate over m, okay, in order to get the moment of inertia of the mass distribution. So in principle, when we do this, we are calculating the moment of inertia of the mass distribution about its center of mass. For example, this point that I indicated here is usually the center of mass. But then you can imagine that when an object rotates, it doesn't always rotate about its center of mass. It can rotate perhaps on another axis that is distant from the first, another parallel axis that is distant d from the first. In this case, you need to apply another theorem that's known as the parallel axis theorem. So parallel axis theorem, okay, which tells us that if you want to calculate, let me call this axis delta prime, if you want to calculate the moment of inertia of a body about an axis delta prime that is parallel to the first axis, in this case I delta, this first axis passes through the center of mass of the body, okay, then I delta prime is going to be I delta plus the mass of the distribution times the distance between the two axes, the two parallel axes squared. So that's what you can see between delta prime and delta. Now, suppose you now want to calculate the moment of inertia of this body about an axis that is perpendicular to delta. So about an axis, maybe that's like this. Let's call it delta prime prime, okay? Then we need to make use of another theorem, this time known as the perpendicular axis theorem. Okay, which tells us that if we have the moment of inertia of a body about some axis, let's call it z, okay, let's just call it z, and then I can relate this moment of inertia to the moment of inertia of the same body about two perpendicular axes. In this case, Iz would be Ix plus Iy. Okay, it's true that on this diagram it's not well represented. So suppose that you have just, let's say, a body. Okay, just anyhow. You have this axis, let's say it's Z. Okay, then you also have X. Let's say this is X. And let's say you have a third axis that comes out of the paper, it's Y. Then IZ is related to IX and IY via this relationship. Here, Z is perpendicular to X and Y. So we can make use of these two theorems to calculate the moment of inertia of a body about really any axis, provided we know its moment of inertia about its center of mass. Okay, then the rest is pretty straightforward. So in the next part of the video, we are going to look at how we can calculate the moment of inertia of a rod. Then in the video after, we are going to see that of a ring, of a disc, and so on. So see you in the next video.